Welcome. This is Dr. Morton again. Just want to, this is the lecture for Monday, the 29th of August, and for logic design. This is for the online section, 2513 01B. So that's the course. Okay, so there is a couple of things. One, I know there's some there was some confusion about the quizzes that are in the book, and let me just say, this is one of the things I found out when I did the book, kind of after I had already done the book, that this was part of the strategy for the publishing company to to increase the pressure to do the book, to buy the book. So I don't know. I wasn't, I learned a lot of things, some of which I might have made different decisions at the beginning if I'd known going into it. But in any event, it is what it is. If you look, so let me just shift over here, and I want to just show. So here's the schedule for things, and so. This is at the end of the syllabus. So if you scroll down to the very bottom of the syllabus, here's the chart. And basically it talks about class day and all that. So today is actually class day 4. And the way it's scheduled right now, the chapter 1 quiz closed on Saturday the 27th, yesterday, because I'm doing this on Sunday. So I'll open that back up, and I'll give anybody that took it a second chance to take it, and I'll change the due date. I'll make it this coming Friday, and that way for folks that were trying to figure out if they had to buy the book or what, would still be able to get that done. The quizzes are at the end of the chapters. I'll show you on chapter 3 here. Today we're going to cover chapter 3, and if we scroll back, and by the way, the homework 1 was due also on the 26th, and so the quizzes close on Saturday, all of them. The homeworks are always due on class days, and both of these are always due at 11:59 p.m. The homework is turned in on Blackboard. The quiz is done in the book itself. Okay, so like I said, I'll give you another shot at the chapter 1 quiz. Hopefully everybody did turn in the homework on Friday. And so let me know if there's a big problem with that. You can turn it in up to a week late, but remember what I said. All you have to get is 50% right. So you're better off to go ahead and turn it in, even if maybe you've skipped a problem or two, that's fine, because you can still get 75%, 60%, 51%, 50%. You'll get full credit. But if you turn it in up to a week late after the due date, you already lose 50%. So now you've got to get 100% to get credit. So you might as well just turn it in on time, even if it's not fully done. And why do I want you to do that? I want you to do that because I want you to keep up with the course. So I'd rather you do some of the homework and turn it in a timely manner than to do all of it and get it perfect, but turn it in late, or maybe not even get it turned in. And of course, why have I come to these conclusions? Well, because I've seen my students that have struggled and done poorly on exams. And then back in the day when I was very permissive, I would let students turn these things in at the end of the semester. And so I just finally threw up my hands and said, you're going to have to turn everything in on time. Just end of story. All right. So that's kind of the deal. Okay, so let's see. What is my problem with the lecture here? Oh, yeah. Okay. So we're going to go ahead and we're going to dive in to the lecture. So let me just do that, and we'll switch over here. Okay, so what I want you to see is that if you look at the book, what you'll see is here we are on chapter 3, and I have a picture that kind of defines each chapter. That was the idea anyway. And here the picture shows a truth table, and we go through kind of some gates, and we get a device. So it's a little bit of a stretch. There's a lot of steps in here we haven't covered yet. but you're going to learn how to take the truth table and turn it into a network of gates, a two-layer network. Okay, here are the learning objectives. I want you to be able to give several reasons for why the tools for digital design are based on binary logic. I want you to be able to write the two-input truth table for the 5 logic gates and or exclusive OR, NOR, and NAND. And also exclusive OR and exclusive NOR. I didn't throw in the exclusive NOR, which is just, there really are 3 different gates, AND, OR, and XOR. And those, if you put an inverter on the output or a bubble on the output, you get the NAND, you get the NOR, and you get the XNOR. We don't use the XNOR too much, but the others we definitely do. And so anyway, this will become more and more clear. But I want you to be able to describe how these gates in their 2-input form work. You should also be able to do 3-input and 4-input and so forth, and we'll cover that. But I definitely want you to, basically, you just have to memorize the 2-input. But it's pretty simple. So you can kind of, once you kind of learn, you can remember it. I want you to implement a truth table be able to implement a truth table with a 2-layer network using inverters, AND gates, and OR gates. And I want you to be able to write the equivalent symbols for AND, OR, NOR, and NAND gates. And we'll go through those. You see, we left the exclusive OR gate out of this, and that's because they're really 2 different fundamental ways to teach logic design. One of those is when you have if you're using the AND and OR canonical form, then we do SOP and POS. There's a whole other way to do it using exclusive OR gates, but that's not how I'm going to do it. So we're not going to really do a lot of exclusive OR gates in this course. They certainly will come up. We'll talk about them, but we're not going to spend a lot of time teaching you how to do designs using the exclusive OR gate, because I think classically and traditionally most of the time we do it with the canonical form of SOP and POS, which is AND input gates and an OR output gate, or input gates and an AND output gate. So that's kind of how we'll do that. Okay, continuing here. So if you look at then, here's a glossary. You just hover over things, and notice I define these. Now if you scroll down here, you'll see there's a video right here. If you click on this basically repeats a lot of what I just covered. And in this video, I sort of covered most of the chapter. So I'm really going to just hit the highlights in this lecture today. And I want you to go back and review this video, which will really cover the whole chapter. Okay? All right. So, yeah. So I want you to understand when we approach logic design, we are going to use switching algebra, and switching algebra is based on constructing expressions using 2-value logic. In this case, zeros and ones, and we don't really mean the number 0 and the number 1. We really mean false and true, or true and false, where 0 is always false and 1 is true. Okay. There's a lot of things you can say about this, but it has served us well for a long time. Now, might this change someday? Yeah, actually it might. There may be a day when we'll decide to go to instead of 2-value logic, maybe 3 or 4 or some other number. But for the time being, all our design tools and all the training that we do for our students is really focused on this 2-value paradigm. Okay, so let me just draw a few things here, and I want to talk about this. So I'm going to switch over so I can write. So the first thing. So remember that 0 just means false, and 1 just means true. And so if we have 2 truths, it's just true. True and true is true. It's not 2, okay? And true or true is still true. It's not 2, because these aren't really 0 and 1. They're just concepts. Now, when we write a logic expression, let's say we write something like xy plus z prime plus w x, something like that. Now, what I want you to see here is we have operators and we have variables, and every appearance of a variable we will call it literal. So let's look at this. So what are our variables here? Our variables are x, y, z, and w. And we have our z is in the form of a z prime. So we do have z prime. And I guess I could have had maybe I could have had a w prime, put that in here. When we look at this, we evaluate this expression based on how many variables do we have. In this case, we have 4 variables, and every appearance of one of those variables is called a literal. How many literals do we have? Well, we have x, y, z prime, w, x prime. Or sorry, I guess that was w prime. So we have 1, 2, 3, 4, 5. We have 5 literals. And then how many terms do we have? Well, we've got this term, and this term. So we have 3 terms. And how many gates do we have? Well, we have an AND gate implied here, x ANDed with y. We have z by itself, and we have w prime ANDed with x. So we've got 1, 2, and then this whole thing has these OR operators, the plus sign. Remember, multiplication is ANDing, plus is ORing. So we have 1 3 input OR gate. So we have 1, 2, 3 gates. And here's how it looks. We would have an AND gate here. We'd have an AND gate here. We'd have z prime all by itself here. And then we'd have 1 OR gate here going out, and that would be f. And these would feed in, as would the z prime. And then we put in x and y here. And we would put in w prime and x here. Now, if you wanted to, I guess you could call this z, and you could put an inverter here. And you could put a bubble on this input and call this w without the prime. But we're not going to do that in this course. It's easier just to use the variables as they are, and not add inverters and stuff like that we don't really have to put in, because it just makes it more confusing. So you would describe this as a 2-layer network. We have 2 input AND gates and 1 output OR gate, and you do have this one degenerative term here of z where it doesn't even have a gate. Now, let me just say, in some cases this can be a problem, because there's always a little delay for the signals when y changes or x changes for this output to change and get down to this input, whereas z is directly connected, so it's going to get there a little earlier if it change and x change at the same time. So there could be a little delay on x, and sometimes we'll put a buffer in here just to slow z down a little bit so it arrives at the exact same time. Sometimes we'll do that. Same with this. All right, so we do have what's called 2 layers. Now, it turns out that any logic expression can be realized with a 2-layer network composed of AND gates with or without inverters, however you want to think about that, and then 1 output OR gate. So anything can be set up that way, and that's how we want to do this. Okay, very good. So we describe this network: 4 variables, 5 literals, 3 terms, 3 gates, 2 layers. And it's important to be able to look at any logic expression and sort out these factors. How many variables? How many appearances of the variables? How many different terms? And then how many gates and how many layers? All right. One thing that's a little confusing is you can see we have 3 terms here, but really that doesn't include the fact that we have this gate here. So we just kind of exclude this output gate from our terms, because we look at this expression. But the whole expression is also a gate. So that's a little confusing, but don't let that confuse you. In fact, I'm less concerned that you spend time understanding how many terms we have. I want you to focus on the number of variables, the number of literals, number of total gates, counting the output gate, and the number of layers. Now, we sometimes do have networks with more layers, but the problem with that is the number of layers, when you add layers, you increase the amount of time for signals when they change to cause a change in the final output. If we have additional layers, that's a whole nother propagation delay of a gate. And so we like to avoid that in most cases if we can. Okay. So next I want to switch to back to the book, and I want to talk about figure 3.1, the first figure in chapter 3, except for the figure at the start, which isn't labeled. And I want you to see that we have this big truth table. It has two inputs, the independent variables A and B, and it has 16 outputs. Now I've labeled those F0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and instead of 10, I put A here because we're using hex. B, F sub B, FC, or F12, 13, 14, 15. You can write the numbers, you can write the hex numbers. I don't really care. I just did it this way so I only had to put one symbol for the subscript. And you notice that we have so there are 16 possible ways you can assign F for 4 rows, right? 2 to the 4, 16. You can assign all zeros. You can make the bottom one 1, a 1 here. You can make it 3, and in fact, I just counted up. So this is this is 0, that's 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 in binary, if you just look at the function. So let me switch back here. So if I just wrote that out, so if my function is, say it's 1, 1, 1, 1, okay, so that in binary is 15. If it's 0, 1, 0, 1, that in binary is 5. Okay, so that's how I did it. So I just made this F5, I just made this F15, or FF, if you will. Okay, so of the various functions here, there are quite a few that really aren't all that useful, and I went over this in the video. The ones that are important, though, are AND, OR, and then exclusive OR here. And then there are 3 more where we just invert the outputs. The OR gate with an inverter is a NOR. The exclusive OR gate with an inverter is an XNOR. And an AND gate with an inverter is a NAND. So let me go down here. There were some other ways you can look at this right here. So this F0 is just always equal to 0, and this FF is just always equal to 1. So those aren't particularly useful or interesting. Here's our AND. Now this is just so this AND gate would represent AB, A ANDed with B. This F2 would be A ANDed with B prime, which is really just adding a bubble to the B input. So it's not really that different. Here, F3 just is equal to A. We completely ignore B. And here, F5 is just B. We completely ignore A. And here, FA, or 10, F10 is just the inverse of B. And F12 is just the inverse of C. I mean, the inverse of A. So those aren't real interesting. And then we have these A ANDed with B prime, A prime ANDed with B, A ORed with B prime, and A prime ORed with B. So there's just very, very minimal differences. So what we're really, the ones that are unique and really different and useful are F1, A ANDed with B, or the AND gate, F6, the exclusive OR gate, F7, the OR gate, so A ORed with B. Here we'd have A exclusive ORed with B, and then the NOR gate, the XNOR, and the NAND, which are just these, the AND, the OR, and the exclusive OR, with inverters on the output, or a bubble on the output. All right, so that's important. Now let's just we'll take a little look here. We'll do a couple of these truth tables, so you kind of know how this works. Okay, so let's say we have an AND gate. Well, so we draw it like this, or you could draw it like this. You have some number of inputs, and here's your output. You only have one output, some number of inputs. Let's say we have an AND gate with two inputs, 1, 2, and an output. And we can draw a truth table to represent this. And so we would call these A and B, and here's our output F. So in our truth table, we'll have A and B at the top, and we'll have the output F, and we'll do 0, 0, and we'll do all possible combinations of A and B. So that's 2 squared, or 4 combinations, 0, 1, 1, 0, and 1, 1. And so then for F, we want F to equal A ANDed with B, just like that. Well, what is that? So for 0, if A is 0 and B is 0, then F will be 0. If A is 0 and B is 1, F will still be 0, because remember, both your A and your B, and there's a little multiplication sign there, both A and B have to be 1 to get a 1. So this is a 0, and this is a 0, and there's a 1. So that's the truth table that defines our AND gate. What if we had 3 inputs? Let's do that again. We'll just do the same thing. We'll do A, B, and C, and we'll do F equals A, B, C. A ANDed with B and C. So now we have to have 8 rows, because we have 3 inputs. 2 to the third is 8. So we do 1, 2, 3, 4, 1, 2, 3, 4, and then we do 1, 2, 1, 1, 1, 2, 1, and 1, and then 0, 1, 0, 1, 0, 1, 0, 1. Okay, and I'm gonna draw a line so we can keep track here. And now, okay, and I'm just going to make this column, and you can forget all this stuff over here. All right, so how does our AND gate work? Well, in this case, F is 0, 0, 0, 0, 0, 0, 0, 0, oh, and it's 1 down there. So the only place where it's 1 is this row here, where all the inputs are 1. It's the same over here, but now we just have one more input. So that's how an AND gate works. And if we had 4 inputs, we'd have 16 rows, and only the last row would output a 1. That's an AND gate. Now, what if we did an OR gate? Well, so an OR gate, we could extend these a little bit. I should have left room here instead of scratching through it like I did. Okay, so let's draw a line here, and we'll say this is an OR gate. OR, and it's going to be F equals A plus B plus C. Well, so it would definitely be a 0 here, because they're all 0, and everywhere else it would be a 1, because at least one of the inputs is a 1 in every row except the first row. And all it takes for an OR gate is any input to be a 1. Now in the exclusive OR gate, it's a little trickier, so we'll do that. Now the symbol for an exclusive OR gate is a plus sign with a circle around it. So in this case, we would say for the exclusive OR gate, so this is OR, and then for the XOR, we would say A, exclusive ORed with B, exclusive ORed with C. And the way this works, it's 0. If you just have one input, it's 1. One input, it's 1. But if you have 2 inputs, it's 0. 2 inputs that are 1. Here you have a single input that's 1, it's 1. Here you have 2 inputs that are 1, so it's a 0. Here you have 2 inputs that are 1. But what about when you have all 3 inputs are 1? Is it still a 0? No, actually it's not. It's a 1. And that's the definition of an exclusive OR gate. Now, I didn't make it up. That's just what it is. Seems a little weird to me, but that's how they do it. So you just have to know this, and then if you have 4 inputs, if all 4 ones are 1, you're back to zeros. So it's a little weird. It's more like an odd even thing. Okay, and then if we want to talk about a NAND gate, then you just invert these. These all become 1s, and there's a 0 down here. So every row is a 1, but the bottom row is a 0. For the OR gate, you put a 1 here, and all these are 0s. And for the exclusive OR, you just invert every single one of these. So that becomes a 1, that's a 0, 0, 1, 0, 1, 1, 0. All right? And all you're doing is putting an inverter on the output, like that, a bubble. And that makes it a NAND gate. Or if it's an OR gate, so that's an OR gate, and if you put a bubble on the output, that's a NOR gate. Exclusive OR gate, we draw like that, and the bubble would be an XNOR, an exclusive NOR gate. Okay, I kind of wanted to go over that. I didn't take as much time on that as the other video. And so I think it's really important that you understand kind of this table. It kind of fleshes out how come we use these gates and we don't have other weird stuff. There actually are other gates people have come up with and have talked about using, but this is kind of where we are for the moment. Okay, now in the video that goes with the chapter I showed you up above, here I'll show you again. You can just click on this link, and the video will start. It's on YouTube, and that'll bring it up. And if you go down here, then one of the things I do talk about in this video is I talk about the codes. This is an old IBM machine that would sort cards. And back before we had computers, we used a lot of these IBM cards with these kind of machines, and there were also printers that could use them. And we would basically hand punch these things out. And like, for instance, we would colleges would use these to do GPAs. Instead of doing it all by hand, they use these punch cards. And the nice thing is they could do alphabetical. They could order these things alphabetically using this machine here, that would sort them into these bins, and that was really a great labor-saving device instead of somebody having to do it by hand. But when you sorted it on one of these machines, it was a painstaking job because you had to let's say you had a 20-character field for the last name and maybe another 20-character field for the first name. You'd have to run things through here a good 40 times to make it work, and maybe more than that, because I think there's not quite enough bins. You actually had to do more than that. But anyway, you could actually alphabetize things, and you could have somebody trained to do it. Now you had to be careful not to drop stuff on the floor, because then you'd have to start over. I talked to you last week. I talked to you about the ASCII 4-bit representations. So again, if you didn't do this over the weekend, I really encourage you, take a piece of paper and just write down the 4-bit ASCII values. So we start with the 4-bit binary values for hex digits. All right. So we have our 16 hex digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And you should be able to write the binary equivalent. Of course, 0 is easy. It's 4 bits, all 0. And 1, 0, 0, 0, 1. And 2, 0, 0, 1, 0. And so forth, all the way down to 1, 1, 1, 1. If you haven't done this, do it today. Make sure you get this knocked out, because you're going to use these the rest of your career. You just need to know them. Okay. So these ASCII codes you don't have to memorize, and I don't recommend you do it. You should just have a chart, somewhere nearby that you can refer to. And if you did your homework, you've already been messing with this, and you had to learn all the ASCII characters so you could get your homework. You could translate that sentence into these ASCII values. But that's a good little practice. I'm not going to ever ask you to do it again, but I want you to do it once just so you'd have a sense, you'd get some level of familiarization. We still use this a lot, especially in the United States or in English-speaking countries, because this works for English pretty well. if you're using other languages, you're going to have to use the Unicode, or you're going to have to use the ISOs, and that's fine. And here's the Unicode, and there's the ISO right here. And I think these will show up. Yeah, and these ISO, it's ISO/IEC 8859-, and then that little N shows up. Now, where do you see stuff like this? Well, I'll show you an example. Here's the integrated development environment. Let's see. Right here. Okay, sorry. Let me turn this on. Okay, yeah. So here's the integrated development environment, and somehow I'm missing this just a little bit. Yeah, somehow I've got this off. Yeah, there we go. Okay, now you can see it. All right, so if we create a little project over here, you'll see where this comes up. You're going to run into this maybe next semester when you do micro. So new project, and we go through here and we click microchip standalone project, and we're going to do it with the, say, a PIC chip. So we'll do the PIC 16F1829, and that's the chip we use in PIC, in Micro 1, this PIC chip. And we're not going to use a header, and then we're going to use maybe our ICD4. That's fine. That's our programmer. You'll use a snap, and now we're going to use this version of MPASM, and here we go. Now notice encoding ISO 8859-1, and there's a whole bunch of other ones. You want to use the -1 because that's the English, that's the American English alphabet. And so, but there are other choices, and you can pick those if you wanted to do it in Spanish, say, or whatever. You still have to spell the words correctly, and it's not going to help you with that. But it would provide you the ENYE, the accents, and some other stuff. All right, and then you give it project a name and so forth. But I wanted you to see that this encoding, this ISO encoding, does come up, and it's used in these things, and it does allow you to use foreign languages. Now, if you wanted to do it in, if you wanted to do some of these other encodings, I actually don't know what you have to do for that. Yeah, X Windows, and some of these I'm sure give you the Chinese alphabets, which I don't know anything about. But we're going to leave it that way and cancel out of this. Okay, so so let me go back here and turn off this. Okay, now what else? So that covers the ASCII. I do cover gray codes, and I think I cover those sufficiently in the video. But I want you to see this is an example of a 4-bit gray code with 16 values. Now, one of the things that's unique about a gray code. Well, let me first do this. Let's switch to the paper again. Let me change this out. All right, so there really are a bunch of different codes that we use, but let's just talk about them. So one of the codes is ASCII, and ASCII will get you a long way for most of the things you want to encode when you're doing some embedded design. But sometimes we do need to use other codes. We're gonna, as our processors get more and more powerful, we'll probably do more video, and so then you're going to have codings like MP4 and MOV and other stuff. We're not going to use any video in Micro 1 because our chip's not really fast enough. We don't have a bunch of cameras. We don't have displays. It just takes it to a whole new level of complexity. We're not going to do that. And there's so many applications where you don't need video. So, but as time goes on, video will be a bigger and bigger part of many of the things we do. So, so these encodings will become important as we go on. Then we also have encodings for pictures. We've got JPEGs. We've got, I don't know, there's a whole bunch of things. I can't even think of some of the other ones. But there's a whole litany of them. and they're all different ways to encode a picture. How you represent the different colors, and how many pixels, and how you encode the information that tells you what kind of a picture it is, things like that. They all have different standards. So these are things we're probably not going to do much in Micro 1, but maybe we'll do some of this in more advanced courses. We might see some of these things, and we'll have to write code and deal with some of these things. Certainly, we have all sorts of AI now that lets us deal with pictures, and we can pick things out of scenes and do facial recognition and read license plates and a whole bunch of other stuff. All right. Then beyond these codes, we also have what we call error correcting. Error correcting codes, we add additional information to the information we're transmitting in order to detect if there's been an error when it's transmitted. Now we do things, we're going to send this digitally, but we can add additional things. So a classic error correcting code is a parity code. And we used to use this all the time when we did dial-up modems, because our phone lines were noisy and we had to dial up with an actual landline phone, and we have a modem, and the modems weren't all that great. Sometimes we actually had to put the handset on the modem, and had a mic and a speaker, and we'd put the handset on. You guys haven't even seen that because all you've seen are cell phones. Well, you see regular phones, I guess. But anyway, back in the day before we had cell phones, we only had regular phones, and that's how we would connect. And so because of these noisy phone lines, we'd use a parity code. And the way that worked, you'd have, say, you'd have a 7-bit ASCII code, and then you'd add a bit. You'd add 1 bit. And that bit would be your 8th bit. And that 8th bit could be a 0 or a 1. And it would depend on whether, let's say you're using odd parity. So if you're using odd parity, you count up the number of 1s in your ASCII code. And let's see, if we go look at this and we go back to our ASCII code here, let's see, where is that? I think it's up here. No, it's down here. So here's our ASCII code, and I don't know if I can make this big enough. Let's see if I can. Okay, for the lowercase b, it's 0110 0010. So I'm going to write that down. So 110 0010. Okay, now I've got it. Let me switch this back. And I think it didn't switch, or did it? Oh yeah, it did. Okay, and then we'll go back. Now, so here's our 7 bits of ASCII code, and then we would say, well, let's count up the 1s. So there's 1, 2, 3 1s. So that's odd. So we're going to make our 8th bit a 0. Done. If we'd only, let's say if we used a C then this equals lowercase b. But if we did a C, that would be 0110 0011. Now we'd have 1, 2, 3, 4. So we'd have to make this a 1, because the ASCII code only uses these lower 7 bits. The upper bit is, we just threw the zeros in, but all of them are zeros, as you can see with the chart. All the 8th bits. All the 8th bits in this chart, all these bits are all zeros because there's only a 7-bit ASCII code. Okay, so I wanted to sort of talk about parity, and then we also have some a thing called gray code. And that's where the shaft encoder comes in, and I do talk about this in the other video. And so, what's a gray code? All right. Well, that's where we have that's where we use this shaft encoder. So the shaft encoder, it's got these rings. In this case, 1, 2, 3 rings. So it's a 3-bit shaft encoder, and you put a photocell kind of somewhere lined up a photocell to read this ring, and this ring. And what you don't want to have happen is, in your shaft encoder, is you don't want to have a transition from white to black, and in this case black to white, all at the same point. So you would want you have your photocells looking at this when this is exactly halfway between these two transitions. These are going to change, but you're kind of in no man's land there, and you can actually have the one, say the outside track could maybe change first, but the inside track could change second, and then the middle track finally last. And as they went through those transitions, you would be very confused because in this part it should be, say, 1 1 0, and here it should be 1 1 0 0 1, and you could have practically any result out of 3 bits. So for that instant, you might flash some changing numbers as you went over that border with your photocells, and you might get any combination. Who knows what you get? You could get all zeros if these two tracks change first and this one changed last, you could read 0 0 0. But what if this track changed? What if this track changed first and these two hadn't changed yet? Then you could get all ones and everything in between. So you would have complete uncertainty for that small instant about where your shaft was. And you don't want that because you're trying to track the degrees of rotation here. And so as a result of that, this would be a very, very unsatisfactory shaft encoder. So what you do instead is you make one that does not have any transitions, that only has a single transition at any junction. Okay? And the way you do that is you use a gray code. And say if we had 4 tracks, we could set them up like this. We could have a transition like this from 0 0 0 0 to 0 0 0 1, and then to 0 0 1 1. Okay, so only 1 bit changes between these two. Between 1 and 2, only one bit changes. The second bit changes from 0 to 1. And from 2 to 3, the first bit changes from 1 to 0, but all the other bits stayed the same, and so forth. So you always have 3 bits unchanging, and you only have uncertainty in a single bit. Now the problem with this is you do have to have a lookup table to figure out which sector you're in, because it won't be in the correct binary order. But with a lookup table, then you get to have a nice little a shaft encoder that gives you uncertainty only in 1 bit. And that's really nice because you never let more than 1 bit change at a time. So that's a gray code. Okay. So that's pretty much what I wanted to cover. I think I'm going to stop here, and we're gonna probably start talking about chapter 4. Oh, I did want to talk about the alternate symbols. Let me do this real quickly. Sorry, I forgot about that. All right, so let's bring those back in. So here are the alternate symbols. We have an AND gate, an OR gate, and I didn't do the exclusive OR gates, but a NAND gate and a NOR gate. Now, if you look at these, you can represent an AND gate by substituting an OR gate with a bubble on all of the inputs and the output. There's only one output. And you can do the same for an OR gate by substituting an AND gate with bubbles on all the inputs and the output. Now, for the NAND gate, you basically, if there's a bubble on the output, which there is in an AND gate, you take it off and you put bubbles on the inputs. And the same with the OR gate. You take off this bubble and put bubbles on the inputs. And you switch out the gate type. So you have you have a NOR gate here, and now you have an AND gate. And you have a NAND gate here, and now you have an OR gate. And here you have an AND gate, and here you have a NOR with bubbles on the input. Here you have an OR gate, and here you have a NAND gate with bubbles on the inputs. The rules for this, and I think I went over those in the other recording too, but let me just do that for, let me just write over here. So again, the AND gate, we can just make this an OR gate, bubbles on the inputs say we have 2 inputs and an output, so bubbles. If we had 3 inputs, we just have to have another bubble. That's all. You're allowed to do these substitutions. Now, what's really great is when you do these substitutions, you can say if you have a connection here, you're allowed to take these bubbles and slide them. You can slide it from here all the way up to here. So now you would have, say, the bubble on the NAND gate, and you might say the bubble's gone down here, and then you might still have bubbles here, and you're maybe going to deal with them. Also, if you have 2 bubbles, you can cancel them both out. They can cancel out. So you can slide bubbles, and you can cancel bubbles, and you can add 2 bubbles. You can add a bubble at the end of each wire. You haven't changed a thing, because they would cancel out, or one inverts and the other uninverts, and you're about to where you were. So you can add 2 bubbles, you can cancel 2 bubbles, and you can slide bubbles around on the wire. You can move them from one end of the wire to the other. All right, we're gonna use that, and we're gonna use graphical methods for converting from one form of a network to another. But we're gonna do that later. But I just wanted to kind of whet your appetite. And then the last thing, and I think I also covered this in the other lecture, so this is going to be redundant, but functionally complete set of gates. So there are a number of different, and we're going to cover this in great detail, but if you look at the the book, you can see this functionally complete set of gates. This notion is that you can represent any logic function with using AND and OR gates, as long as you also have the ability to invert. Or you can actually represent any logic function with NAND, with one layer of NAND, an input layer of NAND gates and one output NAND gate. Or you can represent any logic function with an input layer of NOR gates and a single output NOR gate. So we call it NOR, NAND, NAND, or AND, or sometimes OR AND. So we'll come back and cover this in detail, but I just want you to put this away in your brain that we have these functionally complete sets of gates. For now, we're going to be focusing on AND and or we can also focus on OR and AND. And again, we call the one SOP and the other POS. And we're going to explain that in great detail in our next lecture. With that, we'll quit. Thanks for your attention, and we'll talk to you later.